It started. All right, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about, science and math. And today we are talking about nuclear chemistry, atoms, and energy, Unit 3, for those of you who are sick at home. Okay, so we are learning about radioactivity, and because my smart board is really a dumb board, and it won't let me write on it, I'm going to just use where I wrote on it before, and we're going to scroll. All right, so we have already learned, some of you learned this in your reports. Caravaggio, put away your phone. Time to take notes. No phones. Remember, they're supposed to be in your backpack, in your cubby. Yes? What? You want to do what?
Can you move up?
Yes, you can. Come on. All right. So we already learned this. Who did their element report on uranium? Did anybody in here do uranium? Anybody do uranium in here? Then we might not have heard it in here. The last naturally occurring element is uranium number 92. After that, they're all synthetic. Notice on our periodic table how they are white. That means they're man-made. They're not real. They are kind of real, but they're man-made. They don't occur in nature, okay? They're like artificial sweetener, aspartame. Doesn't occur in nature. So they are man-made. They are not found in nature. They make them at places like the Large Hadron Collider in Switzerland, where they take these atoms, get them going really fast, and smash them into each other. And it makes a new atom, a bigger atom, not a better atom. Now, most elements are stable and not radioactive. And you learned when we did our PhET interactive computer lab, you learned that it was the ratio of protons to neutrons that made it unstable. Do you remember that? How it would shake and say unstable?
What number is that supposed to be? 90?
92. 92. That says man-made and ratio. So it turned out, well, some of y'all told me on lab day that if you had the same number of protons and neutrons, it usually seemed pretty stable. But if you had way less neutrons or way more neutrons, it became unstable. A few of y'all figured that out, okay? And it turns out you were exactly right. Here's a little graph of it. Baylor, are you seeing this? Okay. The red line is the band of stability for neutrons versus protons. If you have way more neutrons than protons, it gives off an electron or a beta particle, which is this cool little Greek symbol that looks like a bee with a tail on it. So today, you're going to get to learn some Greek letters. You're going to feel so smart because you are. Jace, are you paying attention? Right up. I want to see you up here or writing. If you have more protons than neutrons, it will give us something called a positron, which is like a positive electron. So we're going to learn about a little bit of weird stuff that's in the atom that you might not have heard of before. Another thing, if it's got way more protons than neutrons, it will do an alpha particle, which is actually a helium atom. Very weirdly, you can have like uranium just suddenly eject. They're like having a little baby, having a little helium atom. And that's called an alpha particle, and it kind of looks like a fish, little fish. Okay? All right. So here's another little interesting fact. Shh, I'm only going to let you see there if you're quiet. All elements over 83 are unstable and give off radiation, particles from the nucleus. So remember, radiation can cause cancer. It can cook you like a microwave from the inside out. So when you look at elements over 83, those are ones you don't want to mess with. They all are radioactive. Okay? Now, the unit for radiation was named after the mother of nuclear chemistry. Who was she?
Marie Curie?
Yes, Marie Curie. So it's the Curie. It's named after her. Of course, it did kill her. She died of radiation. But they didn't know back then they'd kill you. All right, so the Curie, it's just her last name, Marie Curie. And it's the amount of radiation given off by 1 gram in 1 second. Now, let's talk about one kind of radiation, the alpha particles. It's really a helium atom, and it has a positive charge. This is not a real dangerous kind of radiation. Your skin can block it, so it's not going to get in you and cause cancer unless your skin is broken or if you eat it. You don't want to eat it because then it's inside you and it can hurt you. When I was in college, we did a lab with that, but you're not going to do any labs with any real radiation. You're going to be safe. Okay, my college was a little crazy. We did some radiation labs. Okay, so the symbol is this little fish. See that little fish? That's the Greek lowercase letter alpha. And my keyboard will do Greek, so I had to do that. It's also, sometimes it's just the symbol for helium that we learned in the PhET interactive lab. 4 is the mass, 2 is the number, He is the symbol. Remember how we learned that in our lab? Or sometimes instead of the symbol, they'll put the little fish there instead, the alpha. And it'll have 4,2 alpha. Any questions about alpha particles? I'll tell y'all the story of me and the alpha particles later. Beta particles. Now, beta particles are really an electron being given off by the radioactive element, and so it has a negative charge because electrons are negative, right? You knew that. Tristan, are you paying attention? Okay. I need to make sure y'all don't have on like headphones that you're listening to me. Okay? So the symbol is the Greek letter beta. It's like a capital B with a tail. And sometimes the B is not closed. It gets close, but there is a little gap right there. Sometimes it's written like how we wrote elements in our PhET interactive lab. 0 right there because electrons have no mass. They're kind of like light. And they have no protons, but instead they have, where protons have a charge of +1, electrons have a charge of -1, and they write it down here. So don't get confused, but for an electron, they'll write a -1 down there. And then the little e for electron, or they'll write the 0 and -1 with the beta symbol. And there you can see how sometimes the beta symbol is closed, like right there, but sometimes it's not, like right there. Any questions so far? Is this kind of interesting? Do you feel smart learning about alphas and betas? You should. Because, you know, not everybody takes chemistry. Y'all are being smart. All right, let's scroll up. Can I scroll?
Yeah.
How far can I scroll? All the way? Anybody need this still? Okay. The next one is gamma rays. Alpha, beta, gamma. And you learned this in our last test, that we didn't talk about delta. That was the answer to that question. Okay. Gamma rays are really a type of light. They're a high energy electromagnetic radiation. They're energy. So they have no mass. And you already learned the electromagnetic spectrum. Ronald McDonald is very ugly, extra gross, radio, microwaves, infrared, visible light, UV, ultraviolet, X-rays, and gamma rays. Well, it's the G, it's the gross of Ronald McDonald is very ugly, extra gross. It has no charge. It's only stopped by lead or several meters of concrete. So this is the stuff that's going to kill you in a hurry. It's going to cook you like a hot dog in the microwave oven from the inside out. It's going to give you cancer. There's no stopping it. This is the bad stuff. You probably are not going to turn into the Hulk. The symbol for it looks sort of like a curvy Y, kind of like that. And sometimes it's got 2 zeros next to it, showing that it has no mass and no protons. Any questions about gamma? That's why we have the Hulk drawn in your paper. Okay, another thing that can be given off is a neutron. But when a neutron is given off, just like how electrons aren't called electrons, they're called beta particles. Neutrons have a special name when they're given off as radiation. They're called a neutrino. That sounds like a vitamin, doesn't it? Have you taken your neutrinos? A neutron. So it's like a proton. Its symbol is lowercase n. It's why I was so strict with you about you had to write your elements in capital and lowercase, because lowercase means something else. So capital N is nitrogen, little n is a neutron. Sometimes it is written with a 1 on top for its mass, a 0 on bottom because it has no protons, and a little n. Any questions about that? Okay? There is another one I already told you about on our graph called a positron, and it's like a positive electron. It's sometimes written as a little e with a plus next to it. Sometimes it is written the beta particle sign, but with a 0 for no mass and a plus instead of a minus. Or sometimes it's written a 0 and a plus and a little e. Now, we're not going to do a whole lot with those. The neutrinos and the electrons, the positrons, we do a little with the neutrinos and gamma. But we're going to learn how to balance nuclear equations. But honors is going to have to do a little bit more with that. And then when you take physics, I think you get to learn a little bit more about this again. Okay, so when we balance things, we have to follow the rules. And that's why there's a little policeman in your notes. It's because there's rules about this. We have to follow the law. And the first one is the law of conservation. The law of conservation you probably already learned before in physical science. It says it's the law of conservation of mass and energy. And it says matter and energy cannot be created or destroyed, but they can only be changed from one form to another. A good way I think of this is what you put in is what you get out. Jet, I need to see your eyeballs. We'll make sure you're paying attention and not taking a nap. What? You already have eyeballs? What? I certainly hope so. Okay, so ever since creation, you can't make matter or energy. It can only change forms. Now, in science, we don't really address creation. Religion does, but we don't. We start with the Big Bang, and the Big Bang says all the matter in the universe started off as a baseball. So, of course, about the size of a baseball. So where did the baseball come from? We don't know, and we don't address it. Okay? We just say, well, there's stuff, so it had to come from somewhere. We're not going to say where in science. But ever since it came from somewhere, ever since creation, you cannot make stuff or destroy stuff. It just changes from one form to another. Does that make sense to you? You got it? All right, maybe you'll be the scientist who proves where the baseball came from. Okay, what you put in is what you get out. Now, the next law is the law of multiple proportions. Stop that. Oh, it's rolling. Pretty happy about that. Okay, so this law is that when you have a chemical formula, and you're already used to water being H2O, everybody knows that one already, right? The numbers, like the 2, are always whole numbers. So they're not fraction. Water is H2O. It's not H1 1/2, O 2/3. It's not fractions, and it's not decimals. It's not H2.5, O 3.7. It's whole numbers. So that's called the law of multiple proportions. And the next one is called the law of definite proportions. The formulas for compounds don't change, and the science symbol for change is a triangle. It's the Greek letter delta. See, you get to learn another Greek letter. Delta means change. So from this day forward, Jenny, no phone. From this day forward, you don't ever have to write change or difference in science or math. You can write a triangle. It's accepted. You don't ever have to write it again. Triangle means change or difference. It means subtract. Okay? So water is always H2O. Water is never H2O2. If it was H2O2, it wouldn't be water. It'd be hydrogen peroxide. You couldn't drink it. Now, the hydrogen peroxide you buy at the grocery store is only 3%. And you can, swish your mouth with that if you have an ulcer and you're fine. You won't die. It even says on the bottle you can do it. But 30% hydrogen peroxide will strip your hair white. If you are going to make your hair stripped white, then that's what you use. 100% absolutely is going to kill you if you drink it. Do you understand? You can't change these little numbers. That changes what it is. Tristan, I need to see those eyeballs. Got to make sure you're understanding. Don't drink peroxide. It'll kill you. Okay, so nature likes balance. Nuclear equations must be balanced. Did y'all learn how to balance equations in physical science in 8th grade? Did y'all learn that? Some of you did, yes, and some no. Well, we're going to learn how to balance two different kinds of equations. The first one we're going to balance are nuclear equations, and then we're going to learn how to balance regular equations, chemical equations, because in reality, we're not going to do anything with nuclear chemicals. We're not making any bombs. We're not making any power. So we're going to spend more time with the regular equations. Equations must be balanced. That's why you have a scale drawn in your notes. Okay. Now, you might already know this from physical science, but when you write an equation, the reactants are over here on this side, on your left-hand side. The products are on your right-hand side, and what separates them is an arrow. Do you remember that from physical science? Okay. And on each side of the arrow, it must be equal. Everything has to be equal on each side of the arrow. So we're going to make numbers equal on each side of our atom, on our arrow. Now, we already learned that there are two kinds of nuclear reactions, fission and fusion. Which one is splitting the atom, fission or fusion? Fission, because you imagine a fish, and you split it with your hand, which is the knife. So fission is splitting the atom. It makes a bomb if you've got enough stuff. Now in science, it doesn't sound very sciencey to call it enough stuff, so we have to have a sciencey word, so it's called the critical mass. If you have enough uranium, then you can have a bomb, uranium bomb, like Plankton says in the Friends song. F is for friends who do stuff together. Y'all know what I'm talking about? You might need to watch SpongeBob. Know about the uranium bombs. Okay, so enough stuff is called the critical mass. And then if you have enough stuff, it will start a chain reaction where one atom splits and those two halves go flying off and they each split another atom. And then those atoms split off, now 4 parts, and split 4 more atoms. They then split 8 more atoms. It gets exponentially bigger and you have a giant bomb blowing up a city. Okay? It's also used in our nuclear power plants. And they control it. They use these control rods to keep it from being a bomb. And we'll learn more about that. So fusion is putting atoms together. If you take 2 little atoms and you squish them together, it also gives off energy. And you can also make a new atom. And it's what's happening in the sun and other stars. Who did their report on helium or hydrogen? And you talked about that, didn't you? So you talked about that on the sun, hydrogen, the tremendous gravity of the sun is squishing hydrogen together into helium and making the sun burn. It's a nuclear bomb going off at all times. That's a little scary, isn't it? No life in our planet without it, though. It's all part of the good design. Okay? It gives off energy because E equals mc squared. Matter and energy cannot be created or destroyed, but they can be converted. So in these fission and fusion reactions, matter gets changed into energy. Any questions so far? No? Okay. So this is how you balance the equations. Now don't just write them down. Let's look at them slowly together. Okay, so in our first one, got a little freaky because I touched it. Okay, in our first one, we have the symbol for neutron. And I wrote a 0 there because on Word, it won't let you put a exponent straight above a subscript. So I had to leave it off. So put in your 0. And a neutron can bust and turn into a proton and electron. If you hit a neutron hard enough, it will split into a proton and electron. That's why neutrons are neutral. Let's see if it'll let us get bigger. Yeah, we can get some bigger. Look at that. All right. So protons, the symbol for proton I showed you has a little 1 here. An electron, its symbol has a little -1. Now don't write anything else once you write those numbers right there. Let me show you how the math works. The math is always going to add up on both sides of the equal. Of the arrow is our equal. So let's look at the top. On this side we have 1. And if we look at the top, 1 plus 0 is 1. Does that make sense to you? Let's look at the bottom. The neutron is 0 on this side, and 1 plus a -1, or 1 minus 1 is 0. The bottom works too. How do we feel? Is this math too hard, or can we do this math? Let's look at the next one. So americium is element 95. I would have gotten that off the periodic table. You go look at AM. It's got a blue 95. Everybody see it? It's right next to 94 and 96. It's a few up from uranium. Okay, neptunium is 93. You go off the periodic table. And the subscript for helium is 2. Now, does the math work? Is 95 equal to 93 plus 2? Yes. Is 237 plus 4 equal to 241? Yes. So I can give you this problem and leave some numbers out, and you can solve for the missing numbers. Do you see how it's going to work? Let's look at this one. Iodine is 53, xenon is 54, and an electron is -1. Let's see if it works. 54 minus 1 is 53. Yay. 131 plus 0 is 131. Do you see how it works? Okay, let's look at the next one. Radon is going to undergo fission, breaks down into a different radium to radon, helium, and gamma. So we have 88 on the bottom. So 86 plus 2 plus 0 is 88. 222 plus 4 plus 0 is 226. Can you do it, Jovan? You understand it? You'll be able to do the math? Okay, pay attention. Cobalt, what number should go down there? Somebody look on the periodic table. What number is cobalt?
27.
Where is it? 27. So we're going to write on it. And we'll put it's 27 right there. Okay, what is nickel? You see it right there? 28. So this would go 28 right there. And electron is -1 and a gamma is 0. So let's work on our math. 28 minus 1 plus 0 is 27. 60 plus 0 plus 0 is 60. Okay, so here's a typical problem. The other thing I make you do is identify if it's alpha or beta decay. Do you see how that gave off a helium? It's alpha decay. This one gave off an electron, so it's beta decay. What's this one? It would have alpha and gamma. This one has beta and gamma. Normally it would still be called alpha decay, and that one would be called beta decay. All right, let me scroll up and we'll look at a regular problem. I have to make sure I have time to teach you how to do your homework, but I can't get too excited about this. All right, so here is a typical problem. I would give you that uranium, and I give you the thorium, and you have to figure out what goes in the middle. So you say to yourself, what do you add to 90 to get 92? What plus 90 is 92? Well, it's 2. Well, if a 2 goes there, you know it's helium. And now we're going to check the top. Is 4 plus 229 233? Yes. And this would be alpha decay. Let's do this one together. Okay, so what number is neptunium? Do y'all see it over there?
Is it synthetic or no?
93.
There it is, 93. It's synthetic, it's right above uranium. Good. So 93. And now we need Pu. Do you see it?
94.
94. Okay. So now what is missing here? What is going to make 94 and 93 equal? What do you do to 94 to get 93?
Plus 1. Don't do like 1.
Plus 1 is 1 plus 94, 93.
Minus 1.
You subtract 1. So it's going to be minus 1. Which particle has a minus 1 right there? An electron. And what mass does an electron have?
0.
0. Now let's see if the top works. Is 0 plus 239, 239? Yes. And this is beta decay. Beta decay. Is this going to be easy? So sometimes it goes the other way. What number is copper? Do you see it? 29. And this should be negative 1. Okay, so what's missing here? What do you subtract 1 to get 29? 30, right? So this should be 30 zinc. And now what should the mass be? We don't look at the mass on the periodic table, we do the math. What do you add to 0 to get 66? 66. So is this alpha or beta decay?
Hold on. You lost me at the 66. What's that?
66 plus 0 is 66. Yes, Alexis?
Okay, so it'd be beta if there's an electron.
Right. Alpha if there's a helium. Sometimes they don't fall neatly into alpha and beta. The ones I give you on the test will. That one's beta because of the electron. Now, yes, so that one's beta right there.
What does I mean?
That right there,
No, the one above.
that one, that is an electron. It has a mass of 0 and a charge of negative 1.
I thought it was a.
I know, it's a little confusing. So I'm going to leave these for you to practice by yourself, and I'll tell you the answers later. But let's skip down. I don't want to do them all for you. Don't worry, you'll get to do a worksheet on it. Okay. The next concept is called half-life. It's the time it takes for half of a sample to decay. Now, you know science is always changing. But y'all don't learn the cutting edge science. Y'all learned the science of a few years ago, and you wait till you get to college to learn the cutting edge stuff. So, there's a lot of the cutting edge stuff needs more research before you know it, for sure. Okay, so I'm going to teach you what we believed when I was in high school, okay? And this is what we believed about half-life. We believed that half-life was as steady as the sun rising and falling, and that it was the best indicator of time, of anything that you could tell. So they thought that if you have a sample, you could exactly know the half-life, and the math would exactly work. So they believed at this time that the time it takes for half of carbon-14 to decay is to turn into carbon-12 is exactly 5,715 years, emitting beta particles. Now then, in the last 2 years, they've realized that maybe it's not as steady as they thought, that maybe it's not as perfect as they thought. There were some hints before this. There were some hints because they would use it to date things. You know how you hear in history class or whatever that they found some bones and that they were 4 million years old, or they found some pottery and it was 2,000 years old, or maybe not pottery, but some cooking tools or something like that. And you think, how did they know that? How did they know how old it was? They would use radioactive dating, and they would see how much of the sample is carbon-14 if it had anything living in it, and how much of it was 12, and then they would calculate from that how old it was. But they knew there were some problems for a couple of reasons already. One was, whenever they would test the samples, they always got contamination. Things that were too young, that were younger than they were supposed to be. wait 1 second. And so they said, oh, it's contamination. Well, now our science is so great, we can make sure there is no atom in there that's not supposed to be. You all saw it in the video where they use the lasers to trap one atom. They can do that, and they know no contamination. So if it's still showing up too young, something's wrong. Either the sample's younger than they thought, or the method is not as good as they thought. Another one is they dated some living monkeys of something like 10,000 years old, and they knew those monkeys weren't 10,000 years old. They knew their birth date. They knew when those monkeys were born. So we've known since I was in high school there were some problems. Now we know a little bit more what the problems are. It's not as steady as we thought it was. Yes, Dash? You get 2 passes, and you're within the time. If you want to use one, come sign the calendar. Okay. Any comments about the dating? So, when you hear those dates, I don't say throw them out. I say take them with a grain of salt. That if it says it's so many whatever years old, just know, hey, this stuff's really old. And it probably is really old. Okay, here's your thing. You decide. Okay, remember, it's worth like a drop test at the end. So yeah, you want to hang on to those bathroom passes if at all possible. Okay, let's scroll. Okay, so here is an example. Here is the carbon giving off beta. Now this carbon is turning into nitrogen because 7 minus 1 is 6. It's turning into nitrogen 14. As you will learn as we do these reactions, they can turn into different stuff depending on which particles are being given off. So you'll see the same element doing different reactions, okay? So here we've got our graph here. Let me scroll up so you can see it. Okay, so you start off with 100% of your carbon sample. It's all one thing. And it has undergone no half-lives. So you start off at 100%. After 5,715 years, half of it will turn into something else. You put a dot there. Another 5,000 years go by, and half of what you have now decays. 5,000 more years, half of this is gone. 5,000 more years, half of that is gone. 5,000 more years, half of that is gone. 5,000 more years, half of that is gone. So this is the shape of the half-life graph that you would put on the test. The percents, you start with 100%, then you have 50, then half of 50 is 25, half of 25 is 12.5, half of 12.5 is 6.25, half of 6.25 is 3.125, and half of 3.125 is 1.5625. Now, this is another reason why we realized something was wrong. If things were as old as we thought they were, when we tested them, there should have been no original material left. All of it should be gone. If things were the millions and millions of years old that we think this dinosaur bone is, at this point, there should be no carbon left. It should have all turned into carbon 14. Should have all become something else at this point. And it's always got some carbon there, the original stuff. We've never been able to get with no original stuff in it. And there should be none if things were as old as they thought. So that's what started giving us the clues that something might be wrong with the method. So, but we're going to pretend for this test that there is nothing wrong with the method, that this is perfect. It works like clockwork. The graph looks exactly like this. The percents are exactly like that. Okay? We're going to pretend it's 1985, and we all know about there's something wrong with the dating method. But y'all could grow up and be the scientist who figures it out. There's just some problems with this. I read science journals every day. Yes, I'm that nerdy. So whatever comes out, I read the science news every day. And whatever comes out, I read it and go, oh, that's interesting. So had to give you full disclosure. If I wasn't up on the research, I wouldn't know. But the research is showing that, yeah, something's wrong. It's not as perfect as we thought it was. That makes sense. That's what's fun about science. If we knew everything already, that'd be boring, wouldn't it? If there was nothing left to discover, that'd be boring. So, yay, there's things we don't know. Go us. We're going to learn something eventually. Okay, can I scroll up? You got all of this? All right. Now, isotopes. Okay, yay, we're doing good. I'm going to be able to teach you how to do your homework. Okay, so you already learned that isotopes have more or less neutrons. They have the same number of protons. Some isotopes have special names. In particular, the isotopes of hydrogen. This is not just called hydrogen 1, it's called protium, because it's just a proton. This one is not called hydrogen 2, it's called deuterium. Deuterium, that's how you say it, deuterium. And this one is tritium, hydrogen 3. So those just have some special names you need to learn. Are we good with those? Can I scroll again? Not yet? 1, 2, 3. Protium, deuterium, and tritium. Okay, so you got your digital work. It is the worksheet with the pig on it. That is your worksheet to do for tomorrow, and I'm going to teach you right now how to do it. Yay! Learning more math, and math is great. Woo! Okay. Why are mass numbers decimals on the periodic table? When we just did those reactions, they were all whole numbers, weren't they? Remember we learned no decimals, no fractions. But the red numbers on that periodic table are decimals. Does everybody see what I'm talking about? See those red numbers? The reason why, and we talked about this on our last test, but I didn't test you on it, is it's an average. If you averaged your grades and you made a 98, a 96, and a 50, and you added those three things up, even though they end in whole numbers, you would get a decimal average. If you look at an IC at your grades, and it has a decimal, and then they have it rounded off. Have y'all ever noticed that there's a decimal average of your grade? You ever been right there at the end and had the 89.4, and you're telling your teacher, isn't there something I can do to get you to round it up? Okay, because you saw that decimal, right? So it's a weighted average. If you were going to calculate your grades, you couldn't just add them all. Let's say you got 10 grades. I don't know, do we have about 10 in here? You couldn't just add them all up and divide by 10, because some of them are formative and some of them are summative, and those count different, right? You have to multiply them times what they're worth first. Does that make sense to you? Y'all ever learned how to calculate your grades? Okay. Now, when I used to teach a long time ago, the students couldn't see the computer. The teachers had the computer, but students couldn't see it. So if they wanted to know their grades, they had to calculate their averages. But y'all could just look, and y'all could see the computer, and y'all don't have to learn how to do it. But my old students, they used to have to learn how to do this. And they were good at it, because they would sit there and figure out, okay, if I make a 50 on the final, I'll still pass. So I'm not going to study. That's what they would do. Sit there, how low can I make on the final and still pass? That was the question. All right, do I actually have to study for the chem final? Okay, so this is the kind of problem. This is the problem. Copper has two naturally occurring isotopes. One is copper 63. That means its mass is 63, and its abundance in the world. If you look at all the copper in the world, 69% thereabout is copper 63. And the other isotope is copper 65, and it's the other 30% that's out there. Copper 63 is more common. Does that make sense to you? They base this on current mining data. They're mining the copper mine. They figure out what percent is each, just like how we did with our isotopic pennies and the bags. They figure out what they got, just like how we did using math. And then they know what percent it is. Okay, so this is how you do your problem. I'm going to scroll up. This will be the last thing we learn today, because y'all have done really good doing the lab and... Okay, so first of all, molar mass, where we find that in this class is on the periodic table. See M&Ms? That's why there's M&Ms on our periodic table. Okay, so this is how you do the problem. I want you to list vertically your two isotopes, copper 63 and copper 65. Then you're going to multiply. I would have put a dot there, but I couldn't make Word do a dot floating in the middle. It would only do a decimal down at the bottom. And I want you to know you multiply it times its percent written as a decimal. You remember elementary school, middle school, probably 6th grade, 5th grade. You learned how to go from a percent to a decimal and a decimal to a percent. How you do it is you move the decimal 2 places that way. If you have a percent and you want to change it into a decimal, boys, shh, you move it 2 places. So it was 69%. You go 2 places, whoop, whoop, more fun with sound effects. And it's 0.6917. 30.83% is whoop, whoop, 0.3083. You can remember that because the percent sign has 2 circles on it. That's reminding you to move your decimal point 2 places to get it out of there. Everybody knows how to do that? Jet, I can't see your eyes to see if you understand. Do you understand? Okay. So after you multiply them, you write down the answer. 63 times 0.6917 is 43.5771. And 65 times 0.3083 is 20.0395. Then draw your plus symbol, your equals bar. Remember that? You learned it in 3rd grade. And add them up, and that's the answer. So the average molar mass of copper is 63.6166. Now, if we look at the periodic table, it's slightly different. It's 63,546 instead of 616. The reason why is the numbers come from current mining data and it changes. So if you have an older periodic table, the decimal will be slightly different. Not enough to give you a different answer on a test or whatever, but the answers, the periodic tables, even if you look at newer ones and older ones, those decimal numbers and the decimal numbers on my problems might be slightly different. It also keeps you from just copying down the answer off the periodic table and show me that you really know how to do the math. So I might just change the numbers to make them a little different for you to be able to do the math. Okay, how do we feel about that? Good? Well, I think we put in a good day's work. You may finish your last 7 minutes by getting out that worksheet with the pig on it and start doing it. If you get it all done, you got a free day tomorrow because that's your digital work for tomorrow. All right? Like, share, subscribe. Science is great.